Artificial intelligence can feel like this massive, impenetrable black box, right? Well, today, we're prying it wide open together. We're going to unravel the entire evolution of AI, tracing its path from those clunky, rigid early rules all the way to the jaw-dropping generative tools we're using today. Let's explore how this whole thing actually works.
Here's our roadmap for this explainer. 1. The evolution of AI. 2. Machine learning core techniques. 3. Deep learning and networks. 4. The generative AI revolution. And 5. AI ethics and legal rules. Let's get right to it. Okay, let's dive into this. Section 1. The evolution of AI, from rigid rules to dynamic data. To really grasp where we are right now, we have to look at how AI has historically cycled through massive waves of hype, which were often followed by crushing winters of disappointment. The concept was officially born back in 1956, but it wasn't until the 1980s that we saw the second boom, driven by what were known as expert systems. This basically meant humans manually inputting thousands of logical rules into a machine. Eventually, though, that approach hit a massive wall, leading us directly into our current third boom, an era of data-driven, weak AI that excels at specific, targeted tasks rather than trying to replicate full human consciousness.
So, what exactly was that wall they hit in the 1980s? Well, it's called the frame problem. Just imagine trying to program every single piece of human common sense into a computer. You just can't. There are simply infinite, unexpected events in the real world. Expert systems completely died out because they couldn't adapt outside their rigid, hard-coded programming. We desperately needed machines that could actually learn on their own.
Moving right along to Section 2, Machine Learning Core Techniques, Solving the Rules Problem.
Machine learning was the ultimate fix for that frame problem. Instead of hard-coding every single rule, we just feed the machine data and let it figure the rules out for itself. And this really stands on three main pillars. First, supervised learning, where we give the AI labeled data, using algorithms to classify things into clear categories. Second, unsupervised learning, where the AI finds hidden patterns completely on its own, like grouping similar customers together without us ever telling it what to look for. And third, reinforcement learning, where the algorithm learns entirely by trial and error to maximize a specific reward. But of course, letting machines learn from data introduces a massive, massive trap called overfitting. This is when an AI model basically memorizes the training data perfectly. Think of it like a student memorizing a practice test word for word, but then fails completely on the actual exam. To solve this, we split the data up. This ensures the AI is tested on unseen real-world scenarios so it doesn't just lazily memorize the past. And this brilliantly illustrates how we can push accuracy even further using ensemble learning, which is basically combining multiple models to get a much better result. We have bagging, which runs models in parallel to average out their errors, and we have boosting, which runs them sequentially so each model learns from the previous one's mistakes. A fantastic example of this is how random forests combine multiple, simple decision-making trees to achieve incredibly robust and accurate predictions. Now, figuring out if the AI is actually succeeding is a constant trade-off. We typically use a confusion matrix for this. You've got precision, which focuses on reducing false alarms, and you have recall, which prevents you from missing something important. If you push hard for high precision, you might actually lower your recall, and vice versa. It's really all about finding the perfect balance for the specific problem you're trying to solve. All right, Section 3, Deep Learning and Networks, the Neural Leap. Even with those great techniques, traditional machine learning eventually hit its limits when dealing with highly complex data like images and audio. So scientists looked directly at the human brain to invent deep learning. Let's demystify the math of a neural network here. Step 1, data enters the neuron. Step 2, the network applies weights and adds a bias to that data. Step 3, it passes through an activation function to decide if the signal should actually move forward. And step 4, this is the real magic trick, backpropagation. The AI calculates its own error, sends that error backward through the network, and automatically adjusts those weights to be more accurate the next time around. Doing millions of these mathematical calculations requires an unbelievable amount of computing power. Truly staggering. This is exactly why GPUs, with their thousands of cores for parallel processing, and specialized TPUs became the undeniable engines of the AI boom. Pair that hardware with mini-batch learning, which is processing data in small chunks, and techniques that stabilize the learning process step by step, and you get the perfect balance of blistering speed and extremely high accuracy. But as these networks got deeper and deeper, scientists hit another nasty roadblock, the vanishing gradient problem.
The error signals were literally fading away to zero before they could even reach the earlier layers of the network. The fix? An incredibly simple mathematical function called ReLU. It simply lets positive numbers pass through unchanged and turns negative numbers to zero. Sounds basic, right? But ReLU single-handedly allowed networks to grow to over 100 layers deep without losing that crucial signal.
Which brings us to Section 4, the generative AI revolution: eyes, memory, and creation.
With the complex math solved and the heavy-duty hardware in place, these deep networks stopped just analyzing boring data and actually started mimicking human senses. To give AI eyes, we use CNNs, which scan and extract visual features from images. Models like ResNet push this incredibly deep to handle complex sites. For memory, we use RNNs and LSTMs. They use looping mechanisms to remember past data, making them absolutely perfect for sequential tasks like predicting stock prices or reading a sentence word by word.
Now, while those looping networks were great, they processed data sequentially, one word at a time, which was just way too slow. The absolute game changer here was the attention mechanism and the transformer architecture. Transformers discarded those sequential loops entirely, allowing the AI to process whole sentences in parallel while paying attention to the most relevant words. This specific breakthrough is what sparked the entire generative AI explosion.
This completely transformed natural language processing, or NLP. First, we had word-to-vec, literally converting words into numbers the machine could compute. Then came BERT, which allowed AI to grasp deep bidirectional context in a sentence. And finally, GPT, Generative Pre-trained Transformer, which doesn't just understand text, it generates entirely new, astonishingly human-like responses right from scratch.
But what about generating images? Well, we have two incredible approaches here. GANs work a lot like a master forger and a police officer. The generator tries to create a fake image, and the discriminator tries to catch it. That intense competition creates hyper-realistic fake data. On the other hand, VAEs work by compressing data down to its absolute core features, and then rebuilding it, which is fantastic for generating new variations of existing things. Today, we're seeing all these tools combine in absolutely amazing ways. We have object detection and segmentation making self-driving cars a reality. We have deep reinforcement learning, which allowed AlphaGo to essentially teach itself how to defeat human champions. And now, multimodal AI, which can process images, audio, and text simultaneously to build a truly comprehensive, almost human-like understanding of the world.
Let's slow down for a second for Section 5, AI ethics and legal rules, controlling the machine. As these multimodal systems become unbelievably powerful, we really have to ground ourselves and ask a tough question. As AI perfectly mimics human reasoning, how do we govern its actions, its hidden biases, and its inevitable mistakes? This is the central question every organization is facing right now. Because you can have the best tech in the world, but if the AI crosses legal or ethical boundaries, it simply can't be used in the real world. We are currently navigating a super delicate balance here. On one hand, innovation thrives because copyright law generally permits AI to learn from data without explicit permission. But on the flip side, privacy laws place incredibly strict limits on how personal data can actually be used. And crucially, we're seeing a massive shift toward XAI, explainable AI. People are demanding that AI can no longer be a black box. It needs to explain exactly how it arrived at a decision to prevent hidden bias and discrimination. And that brings us to our final takeaway for this explainer. True AI mastery isn't just about memorizing how a neural network backpropagates or knowing exactly how a transformer works. It's really about deciding how humanity is going to responsibly wield this incredible tool. Are we going to let the algorithm passively shape our future, or are we going to proactively shape the algorithm? Keep exploring, keep questioning, and I'll catch you in the next explainer.